Recall from Chapter 11 that we established a general stability criterion for feedback control loops, stating that a feedback control loop is stable if and only if the roots of the characteristic equation have negative real parts. The characteristic equation for a feedback control loop can be obtained from the denominator of either the servo or the regulator transfer function by taking that denominator and setting it equal to 0. In general, that's 1 plus the open loop transfer function equals 0. Or equivalently, the characteristic equation is the open loop transfer function equals minus 1. If a solution to the characteristic equation is some complex value of s equals a plus jb, with a 0 real part, then that value of s lies on the imaginary axis. That is, it has no real part, and it can be represented by s equals j omega c. And if it's a solution to the characteristic equation, then the characteristic equation takes a value of minus 1. So the phase angle of g at omega c is minus 180 degrees. And the distance to the origin, or the amplitude ratio, is equal to 1. These values for the phase angle and the amplitude ratio of the open loop transfer function establish what we call a critical frequency, omega c, which is any frequency at which the phase angle is equal to minus 180 degrees. And a gain crossover frequency, omega g, is a frequency at which the amplitude ratio is equal to 1. This enables us to establish what we call the Bode stability criterion. For any open loop transfer function, where the open loop transfer function is the product of all of the transfer functions in the feedback loop, usually given by gc, gv, gp, and gm, if there are no poles to the right of the imaginary axis and no more than a single pole at the origin, and if the open loop frequency response has only a single critical frequency, omega c, at which the phase angle is equal to minus 180 degrees, and only a single gain crossover frequency, omega g, at which the open loop transfer function amplitude ratio is equal to 1, then the closed loop system is stable if and only if the amplitude ratio at the critical frequency is less than 1. This method of determining the stability requires that we evaluate the frequency response of the open loop transfer function, but it is superior to the Routh stability criterion that we established earlier because the Routh stability criterion only works when our characteristic equation can be written as a polynomial, and therefore it cannot handle time delays in the characteristic equation exactly. It can only handle them by approximation. The Bode stability criterion, however, can handle time delays because we can explicitly handle the frequency response of time delays. The Bode stability criterion, however, still has some constraints on the open loop transfer function. Let's try applying the Bode stability criterion to see if it works. We'll consider a proportional only feedback controller for a third order transfer function process given here. We'll assume that the valve and the measurement are both instantaneous, that is, they have no time constants or time delays associated with them and are simply represented by gains. The open loop transfer function then is 2kc over 0.5s plus 1 cubed. And we want to find the upper limit on kc, that is, the controller gain, for this feedback control loop using a proportional only controller. Here we've plotted the Bode diagram, that is, the frequency response, for the amplitude ratio of our open loop transfer function and the phase angle of our open loop transfer function for three different values of the controller gain kc, 1, 4, and 20. When the controller gain is set to 1, we can see that the amplitude ratio for our open loop transfer function is greater than 1 for low frequencies. And it has a gain crossover frequency for a value of omega somewhere between 1 and 2. The phase angle plot is the characteristic phase angle plot for a third order transfer function. Notice it has a high frequency asymptote of minus 270 degrees, which means that it has a critical frequency. In this case, the critical frequency occurs at a value of omega between 3 and 4. When we set the controller gain to a value of 4, the amplitude ratio is quite a bit higher. In fact, it's exactly 4 times higher than the amplitude ratio we got when the controller gain was equal to 1. Now when we change the gain of the transfer function, the phase angle plot stays exactly the same. That's because the gain multiplies both the real and imaginary parts, and so it doesn't change the value of the phase angle. This phase angle plot corresponds to all three of these controller gains. Notice that the gain crossover frequency occurs right at the critical frequency, omega c. And if we have the controller gain set equal to 20, then our amplitude ratio is 20 times higher than it was when our controller gain was set equal to 1. The value of the amplitude ratio at the critical frequency here is greater than 1, and therefore the Bode stability criterion says that this feedback control loop will be unstable. In fact, it's unstable for any value of the controller gain greater than 4. Why is that? To understand why the Bode stability criterion establishes a stability limit for the feedback control loop, consider this thought experiment. First, we'll open the control loop at the comparator, and then we'll have the set point input be a sinusoidal oscillation with a frequency omega c. That frequency is equal to the critical frequency, where the phase angle is minus 180 degrees. After initiating that sinusoidal input, we'll have some exponential terms that decay in the signal coming out of the open loop transfer function, which is ym. After those exponentials die out, we simultaneously set the set point input to 0, that is, we turn off the sinusoidal oscillation, and we reconnect the feedback control loop at the comparator. Now we can ask the question, what happens to y? Remember that ym, the measured value coming out of the open loop transfer function, is 180 degrees out of phase with the signal that was coming in the set point. But that signal that's 180 degrees out of phase undergoes a sign change at the comparator. So now it is exactly in phase with the set point sinusoid. If our controller gain were set equal to 4, so that our critical frequency corresponds to the gain crossover frequency, or the frequency at which the amplitude ratio is equal to 1, then this signal ym will have an amplitude that matches the amplitude of our input set point oscillation, and it also is exactly in phase with that input set point oscillation after being multiplied by the minus sign at the comparator. So when we turn off the set point oscillation and simultaneously reconnect the control loop, that sinusoidal oscillation just continues. It neither grows nor decays because the amplitude ratio is 1, and it is exactly in phase with the signal that had previously been coming in from the set point. On the other hand, if the amplitude ratio is even slightly greater than 1, then that signal will be larger than the amplitude of the set point change that was originally driving this. That slightly larger signal will come back around the control loop and again be made slightly larger on the second pass and slightly larger on the third pass. And so it will continue growing, and it will make the control loop unstable when the amplitude ratio is greater than 1. Conversely, if the amplitude ratio is less than 1, then these oscillations will decay each time they go around the control loop. That is, they'll get smaller, and the output signal will converge. For the same open loop transfer function, we could write the characteristic equation and use the Routh array to find the upper stability limit. To do that, we have to multiply out the denominator to find the coefficients of the polynomial. We've entered them here into the first two rows of the Routh array, and we can see based on the last two elements in the first column of the Routh array that in order for this system to be stable, Kc must be less than 4 to ensure that this value in the Routh array is positive. Kc must also be greater than minus 1/2 in order for this process to be stable. The upper bound is the same upper bound that we found using the Bode stability criterion. In this case, both the Routh and the Bode stability criterion are equivalent, but the Routh cannot be used directly if there is a time delay in our open loop transfer function. We'll show this with an example that contains a time delay in the next video.